The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Number 3 on reactor kinetics and control. And what we're going to try to accomplish today is essentially a review of the time-dependent diffusion equation, look at the impact of prompt and delayed neutrons, because without delayed neutrons we'll have a huge amount of difficulty in controlling the reactor. We're going to develop the point kinetics equation, describe some definitions of reactivity, the in-hour equation, which is a solution of the point kinetics equation. We'll talk about some feedback effects, and ultimately reactor control and how all these things interact to allow the reactor to operate in a stable mode. But let me talk first about some key concepts. The time-dependent diffusion equation. What I'd like to do here is quickly go back to the original diffusion equation that we had developed in the previous class. And turn this off here, so that it will link to you what we did. You recall our first neutron balance equation was what? For a critical system was production, okay? Production equals absorption leakage. Now this was the neutron balance equation, and if this is equal, we have a steady state solution. Unfortunately, in time-dependent world, we have a time dependence, which if you put a minus sign here and a minus sign here, you will be able to get a measure of the neutron population as a function of time. And this is, in fact, the equation that we need to solve and we understand relative to how if production does not balance absorption and leakage, we have a change in the neutron population. So if we go back to our original diffusion equation, the production term was nu sigma f, function of r, times the flux at r, minus the macroscopic absorption cross-section, again, is a function of r. And this is, again, what do we call this one group, minus, and I'm going to simplify this, and we can develop this if you wish, the leakage term. So if you go back and look at the one-group diffusion theory, you'll see that this breaks down to a leakage term. Don't want to take the class time to do this, but trust me, it works. If you rearrange this term, and we write it in this way, nu sigma f minus sigma a times the flux, I'll save the subscripts, over d, equals dn dt. Now what is this term, if you remember when we developed the sim one group diffusion equation, what is this term called? Material buckling. Bm squared. And we can write this equation in a way that allows one to simplify it. Let me just draw it over here. In this way. Let me just set it up here for you. If we write the term like this, del squared minus material buckling squared, I guess this is now for a critical system, And this is where we develop this term of material buckling as a ratio of the two fluxes. So if we take and simplify this even further, and we look at the rate of change, 1 over V, these two terms are equal, is that correct? The flux divided by the velocity equals the neutron density. So if we take and work with this term again, and recall that K effective, which is the criticality, is equal to nu sigma F over sigma A plus dB squared. We could plug that into that equation there, and we have defined, in a sense, the term of reactivity, which if, let me just go, erase this up a little bit. So if we go to this expression here, and use that K effective term, bring it down again, sorry. And we define reactivity as the change in K over K, all right? And that, you can relate that to this term as a function of time. We get to a very simple expression relative to the, let's see, down here. Whoops. Nice. Where if we take the, let me just write it up here again so we're on the same page. 1 over V nu sigma F5 minus sigma A5 minus dV squared. All right? Now if we rearrange and divide everything by nu, which is 1 over V, nu sigma F, just dividing by it, okay, equals, and I'm going to get to the reactivity equation in a moment, this equals 1 minus sigma A, 1 minus sigma A plus dV squared times phi divided by nu sigma F. Okay, I'm trying to get us to an expression here that can be reduced to the following terms. 1 over V nu sigma F d phi over phi, K minus 1 over K dt. So we've gotten the time-dependent diffusion equation in terms of reactivity, showing the change in K as a function of time and the ratio of the fluxes. Now this is only good for prompt neutrons, okay? And this term here equals the reactivity term rho. Delta K over K, which is the K minus 1 over K. And we've got that here, where this is now rho. What people sometimes call the nu sigma F term, it is really called the neutron production cross-section. Neutron production cross-section. And it is related to, and I'm going to have to lift this up so people can read it. another term that we want to define, which is called L star, which is 1 over V nu sigma F. Now L star is basically the a relationship relative to the neutron, which is called the neutron mean generation time. And this is going to be important because depending upon this relationship, now we're only talking about one group again, is this will determine how fast the reactor responds to a change in reactivity. And, well, we'll just leave it at that. So when we take this term here and plug it into this equation, where we lost it, when we plug it into this equation here, or more importantly, this equation here, we get the following expression, which is very useful in terms of trying to keep track of the change in the flux as a function of reactivity, L star dt. So we've taken this very complicated neutron balance equation and related it to the reactivity insertion as a function of mean generation time. Does that make sense to you? In terms of how we went from the basic production minus absorption minus leakage to create a reactivity term which gives us a ratio of how the flux changes with time. Now, this solution here can be expressed as a function of time and as a function of the initial condition, the initial flux, as an exponent e to the rho t over L star. So what you quickly are able to see is, now this is for prompt neutrons, that the change in neutron population as a function of time is exponential. And the lower the mean neutron generation time, the faster the change in power, or the change in flux. So this becomes a very important equation in terms of understanding how your reactor is going to perform. And if it was only for the prompt neutrons, we would have a very, very tough time controlling this reactor. Do you recall what this L star might be for a fast reactor? With only prompt, for any reactor, for prompt fissions. What is the neutron generation time here? 10 to the minus 7 seconds. So things go pretty fast when you have to change, when you're only accounting for the fast neutrons or the prompt neutrons to try to control this reactor with this kind of time scale. And the generation time for thermal neutrons is on the order of 10 to the minus 4th seconds, the mean generation time. So we need to figure out a way for reactor control to deal with such a fast time constant. The good news is not all the neutrons are born fast. And the fact that we have delayed neutrons, which we'll talk about in a second, allows us to have some ability to respond to very fast types of neutron productions. There's also another term that I like to describe. It's called a period. You will hear this mentioned a lot. When we go to the MIT reactor, we're going to try to start up, or at least change the power, and we'll be changing the power of a certain period. And the period is defined basically as the reverse of this exponential, in the sense that it's the mean neutron generation time divided by the the reactivity insertion. So this is essentially the time required to change the flux by a factor of E. That's what the period is about. So in the prompt world, we have a relatively straightforward event, but it gets much more complicated because not all of the neutrons are prompt. So in the sense that we have the time-dependent diffusion equation, and we also have the prompt neutron K effective described here by that term on the right. We have the reactivity term, which we've gone through, mean neutron generation time, 10 to the minus 7, the reactor period, and it's also a measure of the time to increase the flux by a factor of E. Now, the good news is that not all the neutrons are prompt, and 99% of them are, and that's at least the time of fission. But we also have fission products, which you recall we talked about, I think, in the first lecture, where we needed to account for how they would affect not only the absorption world, but there are precursors. And as you can see here, there are about 20 precursors that are formed basically for analysis purposes into 6 groups that have half-lives that range from a quarter of a second to about a minute. These are the precursors that release the additional neutrons to allow us to maintain criticality. Okay? And there's a delayed neutron fraction, which is each of these 6 groups has a certain delayed neutron fraction percentage from the precursor group I as a function of the number of neutrons that are produced. So that's what the beta is. And in the next chart, you'll see some of these betas. And the betas basically are of the 6 groups, and it's a function of the half-life. You can see some are 55 seconds to roughly a quarter of a second. And a delayed neutron fraction, which is a measure of the total neutrons you're expecting in the criticality, what's the fraction that are delayed. So on average, roughly 0.65% of the neutrons are delayed, which allows us to control the reactor. And because of this half-life, things are not as the 10 to the minus 7 would indicate relative to the potential for power escalations. So this basically allows us to keep some control over this reactor as we seek to operate it. So when we look at the neutron balance, we have a prompt source. Now that prompt source is relatively straightforward. If you just think about how that would work. If you have a total number of neutrons per fission, that would be what? Nu sigma F, right? That's the total number of neutrons released per fission. Now the prompt source would be what of that? We're calling beta. 1 minus beta. Those are all prompts. And for the delayed source, the next one, what do we have? We have six precursor groups. Let's call them C sub I. And they kind of come out as a function of time. Each one of them has a half-life, lambda sub I. And we need to sum them over all of the i's from 1 to 6. That will tell us when this precursor decays with this half-life, I get 1 neutron, 1 extra neutron. And the cool thing about this is they don't come out all at once, which gives us more time. Next page here. If we then take and try to write the same neutron balance equation, how would we do that? Okay? Now this is reactor physics 2205. I'm sure this is all review, but if we start back with this equation here, how would we take the neutron, the number of neutrons as a function of time? We can write that as 1 over the velocity times the flux as a function of time. So we have the prompt source, and we have the delayed source, and then we have the usual absorption and leakage, right? So the prompt source is nothing but this term here. The delayed source is nothing but this term here, minus the usual happy family of absorption, minus leakage. You now have essentially the full neutron-dependent equation, considering prompt plus delayed neutrons minus leakage, minus absorption, minus leakage. That's the balance. Now, if we were to simply say, okay, that's all we need to know, we're very relatively happy. So we've just written the time-dependent neutron equation. Now, in order to solve this equation, it requires some more manipulations. And let me see if I can do that. Just as a reminder, are we on the same page? This is stuff you've already had, okay? The point kinetics equations basically take the equations that we just wrote here and put them in terms of rho and beta. Let me just describe I'll just write them down here. As a function of time, the neutron balance equation, rho minus beta divided by L star, number of neutrons as a function of time, plus summation I equals 1 to 6 of lambda I C sub I of T. That is the number of neutrons produced, simplifying, or at least summarizing the equation that we just drew and the two equations that we developed earlier. And the concentration of the precursors as a function of time beta sub I L star N of T minus lambda I Ci of T. And this is for I equals 1 to 6. So we have 6 of these equations, each one representing a different precursor group, which is a collection of the 20 or so precursors that can be pretty much lumped by the decay k-times. So again, repeating, this is the mean neutron generation time, the delayed neutron fraction, number density of neutrons, precursor concentration, decay time, and the rest I think we're pretty good with. Now these are called the point kinetics equations. Now if you recall, when we originally developed some of these neutron diffusion equations, we did this in multi-groups. For most applications, even with reactors, they really break it down to a single energy group on kinetics. and even in more complicated computer codes. This seems to be adequate for gross power predictions. Now, to solve this equation, and once again, I'm not going to solve it, the solution to this equation takes the form n as a function of t, as is c as a function of t, is in the form of e to the omega t. And this is like the inverse of the period. So if you take these solutions and you try to solve these 7 equations, you will be able to collapse this into an equation that is the in-hour equation. Let me just see if I can find that here. Sorry. Yes. And the in-hour equation is really an equation for the reactivity I equals 1 to 6 of omega beta I omega plus lambda. This is the in-hour equation that is the solution to these 6 equations and 7 equations, and is used essentially to determine the reactivity insertion as a function of the inverse period, mean neutron generation lifetime, and delayed neutron fraction. We could have gone through here, moved these things around, and solved this equation for reactivity, but that's what the in-hour equation is a solution to this, with the assumption that the neutron population and the precursor concentration as a function of time has this behavior. So that gives you a fairly decent sense of how we want to look at the reactor from the standpoint of time-dependent behavior of the neutron population due to changes in reactivity. Now, do you have any questions about that so far? You're all good with that? Good. Now, if we look at some of the delayed neutron fractions from various types of fissionable nuclides. This is uranium-233, 235. You can see the delayed neutron fraction is fairly high for 235 and quite low for 233 and plutonium. What this basically means is these are more like, the 235 is easier to control. It's got a higher percentage of delayed neutrons. The fast reactors that use 239 and also 233, it could be a thermal reactor as well, but it's much more difficult to control. Things happen faster. This effective delayed neutron fraction term is really because instead of prompt neutrons being born around 2 MeV, the delayed neutrons are about half that energy. So the effectiveness of this delayed neutron fraction is somewhat increased because you've already gone through some thermalization. Okay, so that pretty much takes care of the development of the space, at least the space and time kinetics behavior of a reactor. The next area that I think we'd like to look at a little bit is reactivity insertions. Now, the reactor will follow the point kinetics equations. And as I said, even though it's a one-group model, the reactor generally works quite fine because largely I think the mean free path is large enough such that it operates as a homogeneous system. We have several things that occur, and you might sort of guess that they would occur in this way. There's a prompt jump. Why do you think there's a prompt jump? What does a prompt jump mean? It's okay to speak. It really is okay. A prompt jump. And how would you explain a prompt jump? suppose I made a change in reactivity. What does that do? Where is my change in reactivity expression? Hopefully it's not erased. Let's look at this, the prompt source. This happens when a fission occurs. You'll have an instantaneous increase in the source of neutrons. Sometime later, these will kick in. But the prompt jump will typically occur quite quickly after you make your change in reactivity. And then, as the delayed neutrons start kicking in, it may levelize to go to some kind of an asymptotic period, which is really a function of how quickly the delayed neutrons come into play. Now, suppose your reactivity was a high number. So this is the prompt jump, and this is the asymptotic period due to delayed neutrons. Now suppose we were able to say, let me just do the next chart. The reactor was prompt critical. Do you recall what that meant or means?
The prompt neutrons were sufficient to, the prompt neutrons from one cycle were more than the cycle from the previous cycle of neutrons. So it would be, your time would be almost immediate.
And rho is roughly beta.
Yep.
The reactivity from the prompt jump is equal to beta. If it's less than beta, you will have not a supercritical. If it's greater than beta, you will be supercritical, because there's a lot of activity from the prompt neutrons overwhelming the ability of the delayed neutrons to slow it down. So we also have the period of a reactor is basically this part of the curve. When you move a control rod, you will get a prompt jump. If you stop it, the reactor will continue to increase as the delayed neutrons are produced in terms of power. So when you approach critical, you slowly move the control rods out to a point where you can be on this period such that, and if this is sort of a measure of flux, but it could also be power, you can approach a certain power level that you want to be at by letting the delayed neutrons do your work, as opposed to sort of guessing what this will do. And you have to be very careful about how much rod worth, which is the amount of reactivity that is contained in any control rod or any control rod bank. This is an example of what I was just speaking about. If you look at, let's take one that's relatively small, 0.1% delta K over K, and you can see the prompt jump, and it goes relatively small in terms of the asymptotic period. The higher the reactivity, the higher the period. This is obviously where you have essentially exceeded the prompt critical condition. And there's the neutron lifetime, 3 × 10⁻⁵ seconds, with a beta effective of 0.007. And they measure reactivity in percent delta K over K, which some people at the reactor like to do, or in dollars, which is the amount of that above beta. So $1 is 1 beta. And if you shut down the reactor, or choose to shut down the reactor, you also have a prompt drop or jump. And it also follows an asymptotic period. So the larger the reactivity insertion, the quicker the power reduction. But it doesn't quite stop, because you're still producing delayed neutrons over time. So are there any questions on this part of the reactor kinetics? that need explanation. Because it is, again, this is just a review, but the key points are you can develop a time-dependent point kinetics equation that's useful for a large reactor using single group. You can solve those equations and predict reactor performance simply on the basis of reactivity change. All right, let me now move into reactivity feedbacks. While I erase this part. In addition to the changes in neutron population based on cross-sections and neutron lifetimes, and again, remember the macroscopic cross-section is the key here, because the macroscopic cross-section homogenizes a lot of the material in the reactor, some of which is absorbers, some of which are fission fragments, and they affect how this reactor will ultimately perform. Now we have temperature feedbacks. These are reactivity effects determining how this reactor will respond to various changes. The fuel temperature. The fuel temperature has a couple of components. Obviously, as the fuel gets hotter, the density of the fuel goes down, and what would you expect relative to the reactivity? It should go down. It should. Less fuel, macroscopic, the density of the N number goes down per cc. You also have this Doppler effect, and that's obviously broadening of resonances. And I'll come back to that. I don't know if I have a chart on that. Let me just jump to that chart. The Doppler broadening. And this is typically important for uranium-238. Remember, uranium-238 is roughly 96% of all the uranium in the core. So, and remember we had that, that discussion about the resonances in the sort of mid-energy range, where we needed to get the neutron that was born at high energy down to thermal energy, and they had to go over the U-238 resonance. So if you raise the temperature, you broaden the absorption cross-section to a point where the likelihood of a neutron being captured in U-238 increases, which is a negative reactivity effect, because you reduce the population of neutrons that are thermalized. So Doppler broadening and the thermal expansion of the fuel are negative effects. Now, when does Doppler broadening not help you? Not help you. When the reactor cools down. Instead of, shutting the reactor down, as both the thermal expansion and the fuel and the Doppler broadening basically say, okay, I'm adding reactivity to the core. So if I have control rods that need to shut the reactor down, I've got to be able to compensate for these fuel temperature coefficients that if the temperature goes up, it's good, but if the temperature goes down, it's not good because it'll be harder to shut down. So when I have the scram rods in, I got to make sure I cover the fuel temperature expansion. And as you'll see in the text, the additional reactivity associated that you need to have in the fuel when you go from hot 0 power, cold, to full power, hot, is needed in terms of the enrichment to allow for this negative feedback of fuel temperature to occur. So you have to add excess reactivity defined by those equations that we drew the other day. We also have moderator temperature coefficients and coolant temperature coefficients. And these are basically related to the density of the moderator. Now, what would you think would happen if the moderator density went down in higher temperatures? You're losing reactivity because you're essentially negating the effect of scattering. You're voiding the core. Now, that's a good thing, but again, the reverse is true. Suppose you have an accident, like a steam line break, where you lose the ability to remove heat. The temperature goes up, but you're adding cold water. Now, you're adding cold water because it's not going through the condenser, but you're adding like cold water, you're in fact increasing reactivity. So in a steam line break, you could be adding positive reactivity to the core. Fuel motion. In fast reactors, the rods can bow. And that's included as a good feature because it reduces, again, the overall concentration of uranium in the core, fuel bowing for fast reactors. Fuel bowing in light water reactors is not really that good because it would be, we used to have control rods, we used to have fuel assemblies that were preferentially irradiated, creating bowing. So in places where you needed to put a control rod through the fuel assembly, that was not necessarily easy to do. So from time to time we had to rotate the fuel pins, fuel assemblies, to make sure an equal burn-up, equal irradiation. And then we also have the sum total of all these coefficients for different reactor end up being the power coefficient. So you add all these effects, and when you combine them all as a function of temperature, you have the overall power coefficient. Some reactors have negative fuel temperature coefficients, but positive moderator temperature coefficients. When you in fact add them all together, you will then be able to say the net power coefficient is negative, even though you may have elements of moderator or void where you in fact can have positive. Most designers try to make all of these negative, but it's not always possible, especially in fast reactors where this void coefficient is listed, because as you void a fast reactor, you in fact harden the spectrum and you in fact make it more reactive. So it's a complicated process, but the bottom line is they all interact in an integrated way to determine whether or not you're adding reactivity or essentially removing it. Now here's the sort of the big picture and how all this stuff fits together. If you take a particular reactivity insertion or removal, and that's shown on this slide right here. A lot of things happen in this core. The first thing, there's a kinetic response, which we just talked about, dependent upon mean neutron lifetime, delayed neutron fraction, half-lives, and so forth. And that will give you an instant power response that will do a couple of things. It will raise the power or lower the power, which then does what? Raises the temperature. Neutrons react faster than physical parameter changes, such as temperature. But you will see a prompt change in power, which after a period of time will create more heat, which will then create some of these feedbacks. Now these feedbacks, again, temperature moderator, change in density or dimensions. And then that feedback, let's just say it's negative, will then go back at some later point in time to affect the reactivity, the net reactivity insertion. So what you need to consider and understand when you make a power change, it's just not reactivity alone that's going to determine the future of this particular reactor, but it's this whole feedback loop, which in itself is time dependent. You can solve these things on a systems code where you get the kinetic response and then you bring in the feedback effects, and then you'll be able to track what the neutron population is as a function of time, which people do in detailed analysis of these systems. We're not going to do that because right now we do not have the code to do it. What I'd like to do, though, is kind of go through a quick example. And this just happens to be for a gas reactor, and it shows some of the counterintuitive behavior. And this example basically is peach bottom, where they decrease the helium inlet temperature by 68 degrees, and we'll then just follow what happens. The event is, let's decrease the core inlet temperature. One would think more cooling, everything would be happy. That's not the way it works. What happens basically is the power, as a percentage of full power, it goes up to roughly 112% power. Quickly. Neutrons act faster than heat transfer. we see that the power goes up, and of course initially the colder coolant keeps the fuel temperature down, but then as the power goes up, the fuel temperature goes back up. There is a delay. And as the fuel temperature goes up, the power, in other words, this reactivity would stabilize to a point where the Doppler would sort of come in and kick in and say, okay, that's way too high, and I'm going to try to stabilize it at this new power level. The moderator obviously cools down, adding reactivity, and then as it heats up, again, it sort of stabilizes in terms of a feedback effect. And the temperature of the moderator stabilizes. So the new configuration of the reactor with a coolant decrease is a higher power level. Go figure. Right? So we're now operating, in this case, at 112% power. We've decreased the coolant temperature, and we've got hotter fuel, and we've got roughly, interestingly enough, a slightly lower moderator temperature, which you'd expect. But the fuel temperature is somewhat hotter, and the power is somewhat larger, and the outlet helium temperature is somewhat lower. Not intuitively obvious. And people use the feedback effects to control reactors, like in a boiling water reactor. You increase the temperature, the reactor wants to shut down. In this case, you increase the temperature, and the reactor also wants to shut down. Good thing. That's a positive. But when you decrease the temperature, you have a different result. And any questions on that? So when you start thinking about feedbacks, you need to be able to put it all together. It's not just a simple, well, the Doppler coefficient is negative, therefore everything's all right. Not clear, okay? Because it's a combination of all these phenomena. And that's why that was such a good example. Now, so for reactor control, you have these inherent feedback mechanisms. And the fast ones are the fuel. The slow ones are the moderator, because obviously things need to heat up before you can have a reaction. You also have control rods that are a feedback mechanism, but clearly they cannot act as fast as the fast neutrons. Which is why you need to have rod worth. Rod worth is basically a measure of the reactivity contained in a single rod or in a bank of rods. You do not want to have a rod such that a single rod, if it's ejected, creates a reactivity excursion. Okay? You want to be able to show, and that's what we'll get to the safety analysis section, that the rods are limited by worth such that if a single rod is ejected, you don't fail a lot of fuel. Obviously, it's a local phenomenon, and the fuel design criteria is such that if you do fail fuel, it is within a certain limit. There's a certain instantaneous, huge injection of energy in a local fuel pin, which could rupture the fuel clad if you move this rod too fast or you eject it. So you have limits on the speed at which these rods can be physically withdrawn. That will obviously affect your reactivity insertion rate, which affects your period. And you want to keep your period in a level where it doesn't go exponential on you. And you want to also limit the rod worth such that if you eject one rod, which is one of the design basis accidents, it doesn't create significant fuel failure in terms of energy deposition. The other control mechanism is soluble boron, and obviously that is a slow process. You're not going to add a lot of boron into the reactor quickly because it's just hard to do. It's contained in the coolant. Now, let's talk about this soluble boron and its effect on moderator temperature coefficient. What would you guess would happen if we raise the temperature of say, a pressurized water reactor, and we began to lose density in the coolant? Just give me the phenomenon that occur. A couple occur. First thing that happens is about scattering.
You have less scattering, so the water is less dense.
Okay, which is a negative effect.
Right.
Right?
So you also have less absorption because there's less boron. So that's a positive effect.
So
So it depends on whether or not they cancel each other out or one
Exactly.
or the other.
So in a real reactor, they limit the amount of boron you can have in the boron because of that balance between how much you are thinning out the density compared to how much you're reducing the scattering. So there are actually reactor physics issues that determine how this reactor operates and is designed, which is sometimes forgotten. So we need to be very aware. Now, in a boiling water reactor, we don't have soluble boron. We don't have to worry about that as much. But we do have voiding questions. And the good news about in a boiling water reactor, if you lose moderator, you in fact do decrease the power. But in a PWR, it's not always clear. Let me just sort of summarize by giving you a homework assignment. And it's NEAF Chapter 5, which problems 1, 4, 6, and 9. And also read Chapter 6, which is on depletion effects for the next class. And I guess now we're a little early, but that's okay. Any general questions about what we've done so far in reactor physics? Okay. We started with fissions. We developed the diffusion equations. We understood the basis of absorption, neutron balance. We developed the time-dependent diffusion equation. We looked at the multi-group diffusion equations. We now begin to understand how the reactor is beginning to take shape. And it's beginning to take shape because of the materials that we put into this reactor. The reactor has, when we start looking at it, I don't know if you recall, but as we looked at the hexagonal array of the fuel elements, you had a fuel assembly that had a whole bunch of pins. And inside those pins were this fuel. And we know that there's coolant flowing through the assembly, getting hot. And the core physics of this is understanding the distribution, enrichment level of all these pins, all the materials in this reactor core section, such that we can develop a macroscopic cross sections for fission, absorption, scattering, and we also know that we produce a lot of fission products that alter the composition of this core. So the reactor physics person has to, with modeling exactly the type we did in multi-group equations, the time-dependent behavior of the core based on the position of the control rods, the amount of soluble boron, the degree of enrichment and or burnable poison in the core, such that the reactor can operate for 18 to 24 months. And we recall that after that was over, we're not going to throw away this core. We're going to take about a third of this core and take it out because it's been in the reactor for 3 cycles. And we're going to take what we now understand to be left, which means we will be monitoring the physical behavior based on power, based on flux of every fuel assembly, quote unquote, and saying, well, when I want to rearrange this with fresh fuel, once burned, and then twice burned fuel, I want to bring this reactor back with a fuel configuration and a fuel rearrangement, which we'll talk about next time, that will allow the reactor not only to be critical, but also run for another 18 months. So I've got to know fairly accurately what has gone on in this reactor as a function of time, which is obviously going to be determined by the power level I operate, if I have to shut down for a maintenance outage, or if I have to run at 50% power for some regulatory reason, or I have to move control rods to keep the reactor, critical, in a sense that in a boiling water reactor, since we don't have burnable poison, we have to run the reactor rodded. And in the rodded condition, every month they have to change rod patterns. So they'll monitor the neutron and basically core behavior, and then they'll know whether this area is depleted or not. And then when they put rods in different locations, they'll have to reconfigure and recalculate all of that stuff. So it's complicated, but that's what reactive physics people do, because this is all hugely important, because when we get to the safety analysis, we have to understand the condition of this core and the limiting condition of this core for the analysis. And that's how it all comes together. And as we finish the depletion part, we'll then get into some of the more interesting safety aspects of this. So any questions or comments? You're good? Then I'm good. Thanks.